Thank you very much for the wonderful introduction. Good evening, everyone. I hope you still have patience for one more presentation. Indeed, what I will be presenting today is automated generation of knit patterns for non-developable surfaces. My presentation is structured as follows. I will be giving you a brief introduction into the context in which this research is being conducted. I will be talking about my approach, the results, and finally some current developments and the outlook. So first off, the context in which this research is being carried out. The context is that of concrete construction, to be specific. Concrete is a favorite when it comes to realizing free-form geometry or doubly curved geometry because it can be molded into virtually any shape we want, given a formwork. But if we look at how this really is in construction, we find that it is a labor-intensive, time-consuming, and very wasteful process where the formwork itself needs to be built up on extensive scaffolding and most commonly out of a lot of wood. This results in a gigantic amount of waste because the formwork is only used as a one-off. Additionally, reinforcement in such structures can become very intricate and difficult to place in the traditional manner. So we would want to have a less time-consuming and wasteful approach. The approach we propose would be that of using a flexible formwork system instead of the traditional one, where the approach replaces both the traditional formwork and the reinforcement with a textile one. The most recent example of a structure realized in this manner is the one-to-one prototype of the Nest high-low roof, which is a textile reinforced concrete shell. And it uses a lightweight flexible formwork made out of a cable net as a false and a false work and a tailored fabric as a shuttering. The result is this stunning 20 by 10 by 5 meter structure, which is highly efficient, and it is built on a reusable light mixed cable net and fabric formwork system. And it allows for the reintroduction of an efficient doubly curved thin shell roof without the typically associated high labor costs or resources. Of course, having achieved this wonderful result, we have also learned a few things, and we are already thinking of the next steps. Some of the challenges that can still be addressed are the integration of the different systems on site, so the different layers related to needing to create the fabric formwork, and the patterning that is needed in order to tailor this very specific geometry. In order to address this, we are looking at the textile formation itself, and we are thinking of using knit textiles because they have several advantages. Some of these advantages are the possibility to create 3D structures with minimal stitches. We can integrate channels and grooves. We can have openings with continuous edges, multi-layer or multi-material formations, and of course, also the possibility of integrating straight or woven elements into them. The overall vision for this would be that of creating a structurally informed prefabricated textile, which is very lightweight, easy to transport, and is then easily assembled on site and creates the formwork for a concrete geometry. This is great because it's lightweight, it's easy to assemble and dismantle, and it creates, it enables the creation of doubly curved geometry. So let's look at the knitting itself. Knitting itself is a directional process which is created through the interlocking of consecutive loops. This is done with needles, pulling the yarns through the already formed needles. And it can be, and the unit of the knit that makes it so versatile is the loop. We can abstractly think of the knit material as a matrix comprised of these loops. And if we think of it this way, there are 3 simple operations that enable us to create 3D geometry directly. First off, if we would like to create a widening of the surface, we can create, we can use a so-called increase. And if we would like to create a narrowing of the same surface, we would use a decrease, which is a removing of a loop. In the same fashion, if we were to have directly 3D geometry, so if in this case a bump, what we notice is that the back length is not equal to the front length, and the way we can achieve this is by, again, introducing a number of loops, but in this case an entire row, and this is called a short row. For the creation of these types of fabrics, one would use a CNC knitting machine, which you can see here on the right. And with every pass of this head, it creates a so-called course. The creation of the development of such patterns currently is a manual and tedious process, which is very time-consuming. So it would be desirable to create this in a more automated fashion. Now, one way to do this is to look at it with primitives, because they are simple to imagine, and we have mathematical descriptions which can help us translate these into patterns. However, if we want to use them at architectural scales, and we want to deal usually with very curved or non-developable geometries, these patterns become a lot less obvious. So we would like to create a way to automate this. The approach I'm presenting looks at creating these knitting patterns directly on a given 3D geometry. And the approach is an implementation developed using Python 2.7, and it is based on the Compass framework, which is a computational platform developed within the Block Research Group and will be also later released publicly in November. The implementation itself uses a network data structure, which is a directed graph. The network is made out of nodes, which we will call vertices. These nodes are also connected with edges, and these edges describe the directionality of the knit, hence being warp or weft edges. Lastly, the faces that these networks create represent loops. So the approach can be structured into 4 parts. One of them is patterning. The second part is the generation of each individual course. The third part would be the generation of all the loops within these courses. And lastly, knowing this, the generation of the pattern to be fed to the machine. So let's start with the patching. Depending on the complexity of the geometry, of the input geometry, this can be split into several patches. For generating the knit topology, these patches are not identical to the ones that would be needed to produce the actual fabric. They are just an aid for creating the pattern. So let's have a look at what this would look like for one individual patch. First off, we need to define a loop dimensioning. This loop dimensioning will be then the guide for the course height, defining the course height and the loop width. The next step is also to define a knitting direction, because it is a directional process. And once we have done this, we can go into creating the courses themselves. So for a given patch of geometry, we have a starting edge and an ending edge. With this information and the course height, we create contours. These contours are sampled with the course height to be able to then create an initial instance of the network. This instance of the network is comprised, as mentioned earlier, out of vertices, which know their position in the network with respect to the other vertices, and of edges. For the creation of the courses, what we want to do is add all of the weft edges to the network. All of these weft edges, highlighted here in blue, are added by visiting each node. And then, once we have a look at one of these nodes, the rule for doing so is that each node looks at its closest neighbors either to the right or to the left and no further, finds the closest 4 possible connections, and connects to the one that is most perpendicular in direction. However, in some cases, this can be a less obvious connection. In that case, we would prefer the one that changes least the direction to the previous connection. Once all of these weft connections are added, the courses have been generated, and you can see them here highlighted in red. The ones that do not continue through are what is a so-called short row. Now that we have the courses, we can go on course by course and populate this with the loops that are needed in each course. This is done in a similar fashion as we did with the adding of the weft edges, only this time we want to add all of the warp edges. We sample all of the courses with a loop width this time, and add all of the warp connections. Once this step is finished, we are left with a topology representing the knit, and as you can see, most of the faces are quads, with the exception of a few triangles. And these triangles are the ones that we mentioned earlier, are the exceptions that enable us to create 3D geometry, namely the increases, the decreases, and the short rows. Once we have this topology, we have all the information needed to be able to translate this into a 2D pattern for the machine. We know what the weft direction is, we also know what the warp direction is, and we can translate this into the 2D diagram which is needed for instructions for the machine. So now I would like to guide you through the results achieved using this method. And I will show them again using the 4-directional node from earlier. And I wanted to remind you that the patches that were used to create the pattern itself are not the exact same patches that are needed to knit the actual prototype. Here you can see the pattern that has been generated, and highlighted in red are the so-called short courses. And you can see that both in the 3D geometry pattern and the 2D abstracted version of the pattern to be knit. What you can see here is what happens from going to from a 3D given geometry to a 3D pattern, a 2D, and the knit node resulting from this pattern. What is also interesting to highlight are the same short rows that enable the creation of this 3D geometry, non-developable geometry, without the need for stitching, are the short rows highlighted here in blue. So finally, I would like to give you an overview of the current developments and the outlook. For the fabrication process currently, the node has been done on this electronic knitting machine, which is a Brother KH970, and it is a small-scale, more or less hobbyist machine. However, we would like to investigate how this can be translated to an industrial scale, and we have done so with partners at the Institute for Textile Machinery and High Performance Textiles in TU Dresden, where we investigated how if these patterns are translatable to an industrial process, and we found out they are. However, we do need to have certain small translations for machine-specific processes. Furthermore, I would like to take you back to the construction part, because this is what we're doing it for. So what we have done with the node is coat it with a special cement paste, which has been developed by Lex Reiter, my colleague from the Physics, Chemistry, and Building Materials at ETH Zurich. And this freezes the geometry in a very thin and incredibly light formwork. This can then be used as a formwork for further process, and we have investigated this with the latest result, that of a bridge. The bridge itself is a hybrid between a knit and a bending active system, and it is built up of layers gradually. The knit itself integrates all of the channels necessary for being able to integrate the bending active elements and the cables that help form the geometry itself, and then form the initial formwork. It is incredibly light and easy to transport. The formwork itself right now weighs 433 grams for a span of 2.1 by 1.2 meters. This textile, using the bending active elements and cables, is then shaped into the geometry that we wanted. The same process of applying a cement paste coating is used in order to give the geometry its first thin rigidity, which is just enough for it to hold the next layer in order to create the formwork. After this has hardened, the next layer is set up, and it is just a 5mm layer which will form the stay-in-place formwork. The entire formwork weighs about 20 kilograms, so it is very light and very easy to transport, after which one can pour the concrete in a traditional manner. And this is the result. What I would like to point out is that this needed absolutely no additional scaffolding. The structure that you see here is exactly the structure as it has been built. There were no other supports needed underneath. And this results in a very happy bunch of researchers being able to jump on their bridge. Thank you very much.